Well, you'll notice that that render didn't have any aliasing, and the reason for that is that the filter step has filtering built in. And you can see, if we bring up parameters for filter step, that you can choose the filter type, and you can choose something called the filter width. Now, the filter width is a multiplier on the width of the filter. The width of the filter itself is calculated using the variation in the input here, the test value input, between one micropolygon and the next. So you don't tend to need to attach anything to this width. You don't need to change this because it's automatically calculating how wide your filter needs to be and then multiplying it by this number. So the next thing I want to do is to bring back in our texture, but I want to do it in a way that's varied. So I want to get some random values, and the random node takes a position and produces a random number. So I'm going to create a position by doing a float to vector, and I'm going to feed in these multiplied texture coordinates, and I'm going to feed the result of that into the position. And in fact, I'm going to move this down to the bottom of our window. Now, the random node, unlike noise, produces a single value for each integer range. So if the position is between 0 and 1, say, then it will produce the same random number at 0.1, 0.2, 0.2, 0.4, and so on. And it only produces a different random number if we have, say, 1.2 or 1.3. In other words, for each integer, for each range, 0 to 1, 1 to 2, and so on, it's producing a different random number. Now, by feeding in the values of our multiplied texture coordinates, we're producing a different random value for each tile. And I'm going to create a 3D output, like so. So this is now producing a 3D random number between 0 and 1. And I am going to use that to offset the index to our texture here. So again, I need to take some UV coordinates, and I can bring them in fact straight from here. And I'm going to use an add, like so, and I'm going to feed the result of our random number into the add. And then I'm going to take our texture and I'm going to move that over here. And I'm going to take the result of the add and I'm going to convert it back to floats, like so. And the first value goes into S, the second value goes into T. Now this works because it doesn't matter if this range loops around so that it's above the range 0 to 1, because our texture is wrapped. So if our texture coordinates are 1.5 and 1.5, you get the same bit of the texture as at 0.5 and 0.5. So because our texture is wrapped, we can simply add the texture coordinates. Now, what I then want to do is add a multiply at the end here, and we're going to multiply the two together. And let's see now what that looks like. Now obviously I've still got my mandrel texture here, but we can see we're getting different chunks of the mandrel on each of our tiles. So I want to introduce a bit of variation in the colouring of the tiles. So what I'm going to do is take our vector here, this is just the divided S and T coordinates, and I'm going to add a constant to it, and let's lay down a constant. And the constant I'm going to create is going to be a vector, and I'm just going to add any random values here. And the reason I'm doing this is because I don't want the random number that we produce to change the color of our tile to be the same random number we're using here to position our texture. So now we've got a slightly different input. We're going to have another random, and in this case I just need a one-dimensional output, a single float value. And again, let's move this to somewhere else. Let's move it down here, like so. And then I'm going to use a ramp parameter, and I'm going to want a colored ramp, and I'm going to call it variation ramp, variation ramp. So that should be $OS, and this should be variation ramp. So this is going to form a parameter on our parameter editor, so I'm going to color it yellow, and this is going to produce a random color which is different for each tile. And we want this random color, in fact, to be the thing that appears when we're not in the gaps between the tiles. So I'm going to replace our white node with this. And what we should find, and it's going to be an exaggerated effect because of the way our ramp is set up by default, but what we should find is that we now have a variation in the tone of each of these tiles, and we can see some of them are almost black. So what we've essentially done now is set up the color of our surface, but we don't as yet have any lighting applied to it. Lighting, as you know, has two components. It has a specular component and a diffuse component. The specular component is what produces the bright, sharp highlights. Now, Houdini permits you to construct very complicated lighting models, and I hope in a future tutorial to describe how to do that. But today what we're going to use are the standard lighting models that come by default with Vex. And to be honest, in 90% of situations you can just use these off the shelf without worrying. So let's start by setting up our diffuse component. And there are two popular models for modeling diffuse illumination, and Houdini comes with both of them. They are Lambert and Oren-Naya. There's very little difference between these. This tends to produce a appearance which is more like a sort of eggshell appearance, and this is a flatter appearance. This one also comes with an additional parameter describing the roughness of the surface. So let's get rid of that and concentrate on Lambert. So the first thing we notice is that we've got an input here for the diffuse color. So I will connect the diffuse color that we've calculated into there. We then have this input KD, and I'm going to create a parameter for that. Let's color that yellow because it's going to be a parameter, and that's simply a multiplier for the amount the surface reacts to diffuse illumination. And then we have these two inputs, NN and NI. N is the normal vector to the surface, and I is the vector that leads from the camera to the point we're shading. The small n's before each of these are because we need to produce, or rather connect here, vectors which are normalized. Now don't confuse the name of this vector, normal, with a normalized vector. A normalized vector is any vector whose length is 1. The surface normal is a very specific vector which points outwards from the surface. So although these two things sound similar, it's important not to confuse them. And we can get these variables from our global variables node, so let me drag this over to where we can use it. And we see we've got the vector I and the vector n here. But they have to be of unit length when we connect them here, so we're going to have to normalize them, because we can't be sure when they're coming out of this global variables node that they have unit length. And we can normalize them using a normalize node. So this is the I vector, so we connect that into there, and I'm going to lay down another normalized node and connect the n vector. So that should be our Lambert shading set up. We see it has 3 outputs. First output is the one we're going to want to connect to our color output here. The illumination output simply gives you the amount of illumination without taking into account this factor, this KD factor, and without taking into account the color that you're inputting here into the Lambert node. The third output here, F, is the so-called BSDF variable that's used in PBR renderers. When you have a PBR render, the way the shader works is really quite different from when you have a standard mantra render. And in particular, the renderer needs to know how the lighting model is constructed by following the connections between these F connectors. So in this case, just to ensure this works under PBR, I will want to connect the F output here to the F input of this node here. Let's have a look and see whether that's worked. Well, we see we're getting a much darker render, and that's because there is an angle between the light and the surface, which means that it's no longer just giving us the full surface color, but it's multiplying that by the angle, or a function which depends on the angle of the light. Let's now set up some specular lighting, and we can do that using a specular node. And we can see this has some of the same inputs that we had before, so we can connect in particular the I node, and we can connect the N node there. So we've got a number of different parameters which I'm going to create. As so. And I'm going to color these all. And we can see we've got an input for UVs, so I'm going to need to take all the way from here the UV information and plug it in here. And the reason that it has an input for UVs is because in certain anisotropic shading modes it needs to have the UV coordinates in order to correctly calculate the lighting. Let me pause the video and lay out these parameters.